session, we have covered the thin aerofoil theory for symmetrical aerofoil and also Kutta condition, starting vortex, then Kelvin circulation theorem, and the problems based on thin aerofoil theory. And we will be seeing one or two problems in this session also. And for symmetrical and as well as for cambered aerofoil, we will be seeing some problems. So the main results for thin aerofoil and the lift curve slope is equal to 2 pi, and the center of pressure and the aerodynamic center are both located at the quarter cut point. So the for symmetrical aerofoil, as per the first fundamental in the fundamental equation of thin aerofoil theory, we will be neglecting the dz by dx term. But for cambered aerofoil, the dz by dx term is not equal to 0. And the lift curve slope, the value of lift curve slope is 2 pi, and it is common for all aerofoils. It is same for all aerofoils. So in the session, we will be seeing the thin aerofoil theory for cambered aerofoil. So you all know what is symmetrical aerofoil and what is cambered aerofoil. In the cambered aerofoil, there's a major differences. The camber line and the chord line is not same. And as per thin aerofoil theory, the general equation for deriving the camber aerofoil is also 1 by 2 pi integral of 0 to c. So for solving the cambered aerofoil also, we are using the same equation, 1 by 2 pi integral of 0 to c gamma of psi d psi divided by x minus c equal to v infinity of is alpha minus dz by dx. You all know how we derived this equation. And for symmetrical aerofoil, this dz by this dz by dx will be not equal to 0. But for symmetrical aerofoil, it is equal to 0. So yeah, we all know that the transformation for Fourier transformation, psi equal to c by 2 into 1 minus cos theta, and also d psi equal to c by 2 1 sin d theta, and x also have one value, particular value. We are, by substituting all these things, we will get 1 by 2 pi integral of 0 to pi. The psi is transformed to theta. Therefore, gamma of theta sin theta d theta divided by cos theta minus cos theta naught, that is equal to v infinity into alpha minus dz by dx. So from this equation, we will derive a solution for gamma of theta. Therefore, gamma of theta equal to 2 p infinity a naught into 1 plus cos theta divided by sin theta plus summation of n equal to 1 to infinity an sin n theta. So by substituting this gamma of theta value in the above equation, we will get 1 by pi 0 to pi a naught 1 plus cos theta d theta divided by cos theta minus cos theta naught plus 1 by pi summation of n equal to 1 to infinity integral of 0 to pi an sin n theta divided by cos theta minus cos theta naught, that is equal to alpha into alpha minus dz by dx. So this is the equation for cambered aerofoil. So by substituting the, so we have a integral of sin n theta d theta sin n theta into sin theta d theta divided by, so so for solving, we will taking the trigonometric terms for this. So by substituting the trigonometric terms, we will get a naught equal to this equation, my a naught minus the summation of n equal to 1 to infinity an cos n theta naught, that is equal to alpha minus dz by dx. And also from that dz by dx equal to alpha minus alpha minus a naught plus summation of n equal to 1 to infinity a n cos n theta naught. So here we have two constants, that a naught and a1 a n. So a n will be, if n equal to 1 it will be a1, then n equal to 2 it will be a2. So this is the value for a naught and a1. So from this equation it is clear that a naught, it depends on alpha, that is the angle of attack, and also the shape of the camber. The shape of the camber here, it is denoted as dz by dx. And but an, it only depends on the shape of the camber line, that is dz by dx. So here we need to, the main thing is we need to find the circulation. After finding the circulation, we will be calculating the lift by using Kutta-Jakoskowy transformation theorem. So Kutta-Jakoskowy theorem, L equal to rho v gamma. This gamma is circulation. So first of all we need to find the circulation. So gamma equal to integral of, so for that we are considering the entire vortex sheet from leading edge to trailing edge. So from leading edge to trailing edge, the chord length will be c. So the integral limit is 0 to c gamma of psi d psi, that is equal to c by 2. By substituting all these things, the d psi value, that is equal to c by 2 integral of 0 to pi. That means the c will be value, it will maybe in pi, or it may be in minus pi value. So we are considering it is in the degree is pi. So I am substituting 0 to pi gamma of theta sin theta d theta. And after substituting, we know the gamma of theta value, that is here. So after substituting this gamma of theta value, we will be getting circulation equal to c into v infinity into a naught integral of 0 to pi 1 plus cos theta d theta plus summation of n equal to 1 to infinity a n 0 integral of 0 to n sin theta sin n theta sin theta d theta. So from this one, we know the integral of 0 to pi 1 plus cos theta d theta equal to pi, and also this integral of 0 to pi sin n theta sin theta equal to pi by 2 if n equal to 1 and 0 if n not equal to 1. So after substituting all these things, the gamma circulation value is reduced to c into v infinity pi a naught plus pi by 2 a1. So for your gate exam, only thing is you will be having the MCQ questions, or some questions you need to find the answers. That is also in the form of MCQ only. So you don't need of this kind of derivative parts and all. But what and all you need this, you need to know this trigonometry functions, and also you need to know this gamma of theta value, and also the final equations, that this the circulation value, that is gamma equal to c into v infinity. Because for symmetrical aerofoil also you have one specific formula. For here also we are having one specific formula. This is the formula for circulation. So after finding the circulation, we know that from Kutta-Jakoskowy theorem, yeah, lift, we can calculate the lift, that is L equal to rho infinity v infinity gamma. So here this is the from Kutta-Jakoskowy theorem. After substituting the gamma value here, we will get rho infinity v infinity square c pi a naught plus pi by 2 a1. So in cambered aerofoil, the you need to find the values for these two constants. For every formula you will be you need to find the value for these two constants. After finding the values only, you can get the um, force coefficients and the moment coefficients for cambered aerofoil from thin aerofoil theory. Okay. So here also, after finding the lift, we know CL equal to coefficient of lift, CL equal to L divided by half rho infinity v infinity square. Yes, that is S equal to C into 1. Therefore, by substituting, we will get C can get cancelled. Rho infinity, rho rho infinity get cancelled, V infinity square get cancelled. So remaining terms will be pi into 2 A0 plus A1. So then this is the final equations for CL, for finding CL. That is after substituting the A0 and A1 value in the equation will be CL equal to 2 pi alpha plus 1 by pi integral of 0 to pi dz by dx cos theta naught minus 1 into d theta naught. So after finding the CL value, this is the formula, and after finding the CL value, you should find the lift curve slope. So the mainly for in thin aerofoil theory, we will be finding the main thing is to find the lift coefficients. That is L, CL value, then lift curve slope DCL, DCL divided by D alpha, and also then moment coefficients. That is M about M suffix LE. That is moment about the leading edge and moment about trailing edge, then moment about quarter chord point, that is C by 4. These all things we will be finding in thin aerofoil theory, both for symmetrical and unsymmetrical aerofoil. Except these things, one more equation also we will be finding, or one more term also we will be finding, that is a location of center of pressure. Because apart from symmetrical aerofoil, in symmetrical aerofoil, both the center of pressure and aerodynamic center is at the same points, or the location is at same. But for cambered aerofoil, the aerodynamic center and the location of center of pressure is not same. The center of pressure, it varies with the angle of attack. When the angle of attack increases, automatically the center of pressure is also increased. So the location of center of pressure is changed. So because of the change in center of pressure location, we need to find the location for center of pressure, that we will be seeing the subsequent slides. So, and one more thing, for symmetrical aerofoil, there won't be any zero lift angle of attack. That is alpha L equal to 0 is will be 0 for symmetrical aerofoil. But for unsymmetrical aerofoil, it is not 0. There will be some values for zero lift angle of attack, alpha L equal to 0. But the value will be a negative value. So I'll be asking one questions to you. I'll type those questions so that you can understand. Or I'll ask. So for a cambered aerofoil, the pitching moment coefficient of a the pitching moment coefficient for a cambered aerofoil is whether it will be positive, negative, or 0, or none of the above things. So the answers are: one is positive, another one is negative, another one is equal to 0. Okay. So after completion of this thin aerofoil theory, I will be asking the question once again. Anyone please answer the question. Okay. So we will be finishing this first. So for thin aerofoil theory, the alpha zero lift angle of attack is not equal to 0. Zero lift angle of attack means when the angle of attack is 0, there will be some amount of lift, and the amount of lift produced by this angle of attack will be a negative value. That is called zero lift angle of attack. Then the CL equal to, for this, the CL equal to dCl by d alpha. That is the dCl by d alpha is a lift curve slope. We all know the value of lift curve slope. So lift curve slope is the value of the lift curve slope is 2 pi, and remaining things alpha minus alpha L equal to 0. For a symmetrical aerofoil, these things will be 0. Therefore, the terms will be there won't be any zero lift angle of attack. But for unsymmetrical aerofoil, there is a definite value for this. So as per thin aerofoil theory, it produces a value for a zero lift angle of attack. So in order to find the zero lift angle of attack, this is the formula. So we'll be solving one type of problem for this zero lift angle of attack in the later session. So moment, then the next thing is the moment cohesion. So now you all know how to find the lift of cambered aerofoil using these formulas. Then next thing is to find the moment cohesions. So there are three types of moment cohesions we need to find. One is the moment about the leading edge. Second one is the moment about the quarter chord point. The third one is the moment about the trailing edge. And last thing we need to find the location of center of pressure. So not the formula for moment about the leading edge is minus of CL by 4 plus pi by 4 of A1 minus into A1 minus A2. So the moment question about the quarter chord point is Cm C by 4 equal to pi by 4 into A2 minus A1. As I already told that the quarter chord point is not the center of pressure of a cambered aerofoil, because the aerodynamic center is at the quarter chord point, but for cambered aerofoil the center of pressure will change. So therefore the quarter chord point is not the location for center of pressure. We all know in the last class, it's last session itself, I explained about the center of pressure. Anybody? Hello, students? Anyone please respond, because I don't know whether I am audible to everyone.
Am I audible?
Hello.
Hello.
Yes.
Hello, sir. Am I audible?
Yes.
Hello,
Oh,
yes,
okay.
sir.
Yes, sir. We are able to listen to you, sir. Actually, center of pressure, you explained in the previous class that it's a particular point in the airfoil where the lift actually acts.
Yes. The forces actually acts on the particular point. So for once again, I'm repeating these things. Sometimes they will ask the concepts. So in your 2018 question, there was a 18 gate question. There was a question from this cambered aerofoil. That only I asked for some moments before. The question was the pitching moment of a positively cambered Naka aerofoil about its leading edge at zero lift angle of attack is. Can you able to understand my question? So I will repeat the question once again. Pitching moment of a positively cambered Naka aerofoil about its leading edge at zero lift angle of attack is. So they are asking pitching moment questions, that the pitching moment of a positively cambered, that is a cambered aerofoil about its leading edge. The moment question is about its leading edge. So Cm leading edge. Cm leading edge formula, then at zero lift angle of attack. Okay. So we have seen the moment question Cm leading edge formula. The formula is minus Cl by 4 plus
Excuse
pi
me,
by
sir.
4 into A1 minus A2.
Sir,
That okay.
sir, may I know what is the value of that A1 and A2, sir? I forgot.
So actually, it has some formulas. There is an expression for this A1 and A2. That
So
are
please,
two
please do tell.
constants we need to find.
I will just note it down, please. We will.
Okay, okay. Just note it down. So A not equal to just note it down.
Yes, sir. 1 second, please.
Okay, fine, no problem.
So can you please go to the previous slide once, sir? Sorry. Yes. Yes, sir.
Okay, fine. So the question what they are asking is the moment about the leading edge when the condition is in zero lift condition. The angle of
It
attack
will be
is
positive, sir.
yeah, no. It is negative. It will always be negative, because the zero for a zero left angle of attack, the value is negative. So the pitching moment coefficient also the value will be negative only. Okay. Then Okay, fine. So in order to find the location of center of pressure for cambered aerofoil, this is the formula. So in last class you have asked one question, no? How we can find the mean camber line and lift coefficients because of the by using the mean camber line equations and all.
Equation, yes, sir.
Yes, the answers are we will be solving on problem relevant to that. The d set by dx on term is there now.
Yes, sir.
So I have explained about a d set by dx term. This term is the denotes the shape of the mean camber line only. Okay,
Denotes the shape of the mean camber
shape
line.
of the mean camber line. So what they will give means they will give a equations for this d z by dx term. We need to, or they will give like this z by c, z by x, like this. They will give some equation, and they will ask us to find the lift coefficient, zero lift angle of attack. From this equation, they ask us to find other that lift coefficient values, moment coefficients values, and also the center of pressure values. What we need to do is we need to derive some expressions by using this equation, and after that, because they will give some values like this for a1 also, they will give some values. They will they give one equation. I have put a problem for this. I will show. Okay. So it's z by c. This is the mean camber line equation. Okay. So z
Okay.
by c equal to 0.25 into 0.8 x by c minus x by c the whole square. This is the equation. For up to the limit is 0 to 0.4. Then 0.2, 0.4 to 0.1, we have another one equation. So we need to solve this problem. Based upon the this only, we will get uh, the dz by dx value, and after that we will be finding the a1, a0, a1, everything other values, and we will be substituting the a0 and a1 value and find the alpha L equal to 0 value. See, here we need to calculate the alpha L equal to 0 value, but for other things they can calculate lift values, drag value, lift values, and moment values also. Okay.
Okay, sir.
Okay. So upon substitution of this cm leading edge value, this cm leading edge is minus cl by 4 plus pi by 4 into a1 minus a2. Upon substitution, we will get the final equation for the location of center of pressure is equal to c by 4 into 1 plus pi by cl a1 minus a2. So xcp equal to c by 4 into 1 plus pi by cl a1 minus a2. Okay. So these are the formulas. So if you want to note down, I will show you the formulas. Have you all note on the previous formulas and all, or it may be in a aerodynamics book also.
So
If you
but
want,
this
you can note
PPT,
it. Uh,
this PDF will be shared, sir.
yes, yeah, this PDF will be shared. This video is also shared, so no problem with that. You can um, note it down later also. But if you note down now, it is wise. Okay.
Okay.
Okay. So, so these are the results for thin aerofoil theory for cambered aerofoil. So CL equal to 2 pi into alpha plus 1 by pi integral of 0 to c. So in last session for symmetrical aerofoil, we found that CL equal to 2 pi alpha. But here we are having a specific equation for dz by dx and alpha values. By substituting all those things, we will get the final CL value. Say in the same way, lift slope, in the last session also told, in this session also I have explained that the lift curve slope, whatever the aerofoils may be, it won't change. It will be constant for all aerofoils. Okay. And another one important consideration is, or result is, the aerodynamic center is at quarter chord point, that we all know. But the center of pressure only, it varies with lift coefficient, because when angle of attack changes, automatically lift increases. But if we so if lift increases means angle of attack, if the angle of attack is changing, the center of pressure is also changing. So lift increases means also the center of pressure is changing. Okay. Oh, fine. So So we'll be solving some problems now. So this is the problem. Here you can see. Consider a symmetrical aerofoil at an angle of attack of 4 degree. Consider a symmetrical aerofoil at an angle of attack of 4 degree. Using thin aerofoil theory, the magnitude of moment coefficient about the leading edges. So you need to find the moment coefficient at the leading edge. So can you able to find this problem?
We'll try to solve, sir.
Okay. Let's say take on 5 minutes or 10 minutes and try to solve this problem. If you have any doubt, means just ask. I will explain or I will solve it. Okay. So the given data here is angle of attack is 4 degree by thin aerofoil theory, and it is a symmetrical aerofoil. It is not a unsymmetrical aerofoil. It is a symmetrical aerofoil, and we need to find the moment coefficient at the leading edge. Okay.
Sir,
Yes.
we have to convert alpha from degree to radian, sir.
Yes. That was the important thing you need to do.
So actually 1 degree is equal to 57.3 radians, correct, sir?
1 degree equal to
57.3 radians.
yes.
Am I right, sir?
1 is 57.3 correct only. That rise to -1 it will come, I think so. That is 5 into 1 divided by 57.3, or else you just put like this, pi by 180.
That's what, pi by 180. It's 4 into pi by 180.
Yes.
Okay. So are you sure it's pi by 180 or 180 by pi? Sorry, I forgot.
Pi by 180 only.
Okay. So I'm getting it to be minus 0.1096.
Number you can see the answers like this now. A equal to 2 pi, B equal to pi, C equal to pi square by 60, D equal to pi square by 90. This is pi square. This is not a
So
pi
what is
cube.
the value of A1 and A2, sir? Means is it a constant, sir, or
See, one thing we need to remember this. This is a symmetrical aerofoil, so no need of that to find the A1 and A2. So here we are solving for a symmetrical aerofoil only. So I will show you the formulas for a symmetrical aerofoil. For symmetrical aerofoil, moment coefficient about leading edges equal to minus
pi alpha by 2.
C.
-1, sir, answer?
No.
So
C.
minus pi alpha by 2, sir.
Minus pi
Alpha by 2.
minus pi alpha. No. See, I'll be showing you the formulas. So Cm leading edge is equal to minus Cl divided by 4. This is Cl, lift coefficient. Okay. So first we need to find the Cl value. So Cl equal to what? In the above one equation is there now. Pi alpha equal to Cl by 2. So from that Cl equal to 2 pi alpha. So we need to substitute first Cm leading edge is equal to minus 2 pi alpha divided by 4. So Cm leading edge is equal to minus of 2.
So actually, sir, like anyway, both the answers will be right only, sir. CM leading edge minus pi alpha by 2, or we can write as minus CL by 4. Both are going to be the same thing, sir.
Minus Cl by
So actually, in the previous slide, if we move, we can see there's one more formula. CM leading edge minus pi alpha by 2.
yes. Okay.
Minus pi alpha by 2. I could see somewhere. Yes, it is given in the down, minus pi alpha by 2. So we are having given the angle of attack, pi and 2 are constant, so we can convert it into radians and we can set it to be minus
Yes,
0.1096.
yes. Okay. But we need to find answers like this now. You no need to convert that pi value in the and multiply the pi value and all. Just to see the answers are 2 pi,
The
pi,
pi
pi
square
square.
by 90.
Pi
Yes,
square by 90, sir.
yes, pi square by 90. That is the correct answer.
So
Anyone,
it's a minus, no, sir.
Yes,
minus, you
sir.
need to,
Minus is coming,
no,
sir. The answer
no
is
need.
absolutely same, sir. With minus 0.1096. Magnitude is same, but the
Yes,
minus sign is coming, sir.
no problem because they are asking only magnitude, no need the direction and all.
The
So no
magnitude
problem.
of the moment.
Only they are asking magnitude only. Okay. So no problem. Anyone, please share the the solved problem that I will be seeing.
How can I share, sir?
One second. So just well, you don't have that. It was in a mobile or it was in a.
In laptop, how can we share, sir?
So you have to take a photograph. It was a big process. No problem. So everyone got the answer. Everyone.
Yes, sir.
Okay, fine. So shall we move on to the next problem?
Yes, sir.
Okay. Next thing also, same type of problem only. So consider a. So can you able to hear me? Please reply anyone.
Yes, sir.
Okay. Thank you. So the third problem is also consider a thin flat plate at 5-degree angle of attack using in the thin aerofoil theory. The lift coefficient is, so by using thin aerofoil theory, you need to find the lift coefficient value. Can you able to find this problem also?
Third option,
Same
0.5.
same type only. It was easy only.
0.5485.
Okay. Everyone got the same answer?
Yes, sir.
Okay. Fine. So we will be seeing some concepts and we will be solving one problem for cambered aerofoil, because it is a somewhat a bigger problem. We will be seeing in the later. Okay. So as I told before, that aerodynamic center and center of pressure is some variations for cambered aerofoil. The center of pressure, it varies with the angle of attack. As the lift increases, the center of pressure is also uh, it moves to somewhat closer to aerodynamic center. But if the lift decreases, it moves away from the aerodynamic center. And for symmetrical aerofoils, the aerodynamic moment about the aerodynamic center is 0. That you know. Um, for unsymmetrical aerofoil, it is at the quarter cut point. Then you have heard a concept like infinite wing and finite wing. Have you heard about that? This is one of the important questions some asked in one asked in 1 year of gated questions only. That is infinite wing. What is infinite wing? Anyone? So in the slide itself, we have answers for this. So finite wing is a 3-dimensional wing. There is a normal wing of an aircraft. Infinite wing is there is a this is we will consider it as an aerofoil. The 2D section of the cross section of the aerofoil is a infinite wing. The infinite means there is no end. So for infinite wing means it is we will consider that as an aerofoil. So you all know. So aerofoil, over the surface of the aerofoil, we will be having when the flow there is a flow induced over the surface of the aerofoil. For the top surface, we will be having a low pressure, and from the bottom surface, we will be having high pressure. Because of the pressure difference only, we will be getting some lift. But as per the circulation, there will be when it is at rest, the circulation will be 0. When it is at motion, the circulation it begins. There will be a circulations around the aerofoil. Because of the circulation, we will be getting some amount of lift. That's why for a symmetrical section also, the the boundary layer or the not a symmetrical section, a cylindrical section also, when in the cylindrical or a cylinder, when it rotates and in kept in a flow, there will be some amount of some changes. There will be circulation around the cylinder, and we will be getting small amount of lift. So here in the figure, you can see the finite wing. So it's the top of the top view of wing, and you can see the velocity, free stream velocity is v infinity, and the streamlines are the flow over and under the aerofoil. The bottom surface of the aerofoil is noted as dashed lines, and upper surface is the top surface of the aerofoil is seen here, floor. Then this is the root of the aerofoil, and the root is denoted as CR, and the tip is denoted as CT, and the span of the wing is B, and the area is S. S is C into 1 for unit span. Okay. So why we are
Hello, sir. Sir, why it is known as like a finite wing and infinite? Hello, sir. I'm audible.
I couldn't
Hello,
get
sir.
you.
I'm audible.
Yes, yes. Once again, repeat the question.
Why it's yes, sir. Why it's a 3-dimensional wing is known as finite wing. 2-dimensional wing is known as infinite wing.
Yes,
Is there
sir.
any specific reason?
No. So you have done any experiments in wind tunnel? Have you done any experiments in wind tunnel?
Yes.
The flow or an aerofoil, you will say the flow or a aerofoil, not the flow or a wing. Why you have considered like this? Do you know?
Yeah.
And the aerofoil section will be kept at the one end, and throughout the test section, it connects from one end to another end. Have you seen that? In sometimes only they will give a small.
Yes, sir.
If the plan form is small, they will kept in inside the wing, and the inside the test section, and we will be having more space, because the finite wing, they are considering the infinite wing is as a aerofoil. So if it connects from one end to another end, that means the one end of the window to another end of the window in the test section, or the one end of the mirror to another end, then it will be act as a infinite wing, not a finite wing. The finite wing means it will be having some definite length and all. Okay. So the aircraft wings and all, it will be it acts as a finite wing, but the aerofoils, it will act as a infinite wing. That's the main difference. Okay.
Okay, sir.
Oh, fine. The next thing is wingtip vortices and downwash. We have seen this downwash and wingtip vortices in the last session also. Once again, I will repeat, because wingtip vortices and downwash only will be focused for the finite wing theory, and we will be seeing that why Prandtl lifting line theory is kept in the finite wing theory. What is finite wing theory? That we will be seeing how the lift is distributed over the surface of the aerofoil or surface of the wing. That we will be seeing in the upcoming sessions. Okay, so wing tip vortices or trailing edge vortices. We are what is trailing edge? So in a wing, we will be having a wing or aerofoil, whatever maybe. We will be having two sections. One is front surface or front edge is called the leading edge, and the yeah, trailing edge is the end where uh, the symmetrical or cupped angle will end. Okay. Hello. Hello.
Yes, sir. Tell me, sir, please.
Yes, sir.
Sorry. No. There was a disturbance. That's why I asked.
Oh,
There was a disturbance in between. That's why I asked. Okay. No problem. So here we are going to see about wingtip vortices, how wingtip vortices are formed. So normally the aerofoil over the wing, when the flow over the wing, the flow is split into two halves. One is one half it will move towards the top surface of the aerofoil, and other half it will comes on the bottom surface of the aerofoil. And uh, what will happen at the trailing edge? They will intersect. They both will get intersect, and it will form a curl. It will form a curl, and what is formed at the trailing edge of the session. And but at the rear end, at the tip of the aerofoil, what will happen means it will the flow under the surface of the aerofoil, it will try to come up. So because it tries to come up, it will form a whirl, or it will form a curl around the tip surface of the trailing edge, and it forms a vortices. This vortices are formed at the wingtip is called wingtip vortices. And because of the downwash the vortices are move somewhat backward. That is called downward. The downward component of velocity is called downwash. Okay. So yeah, have you done any computational analysis
Sir,
in ANSYS and
one
all?
second.
Yes.
Excuse me. So, can you please explain what's called downward component? This one I'm having a doubt for a longer time, sir. Downwash. What is the exact meaning of it?
Yes. The last session also I explained you. So
Please, once again.
downward means, so when the flow is over the aerofoil, at some point, maybe at the whatever point, at some point, what will happen? From bottom surface of the from the bottom surface, air tries to move upward, and it will form like this. I will just show you. So this is the aerofoil. The flow will be coming like this. It will move like this, and what will happen at the trailing edge? The flow will try to move like this, move upward, and flow over the top surface also. It will move here. When it reaches the trailing edge, what will happen is these things will intersect, and it will form a curl or vortices at the trailing edge. because of this force, what will happen? There is a downward movement. This downward movement, it will movement of air. It tends to move the vortices somewhat backward. It won't make the vortices stagnant at the trailing edge. This is called downwash. Some some downward movement of air because of the curved slope. Okay,
Okay,
this
sir.
is called this is called downwash. Then so
Sir, what is significance of downwash?
hello, I couldn't hear you. Hello, what?
What is significance of downwash?
See, I couldn't hear you.
Sig-
Your
Significance of downwash.
significance of downwash. So downwash is mainly for
Yes.
reducing the trailing edge vortices. That you will be seeing a wash in terms because of the angle of incidence and all. There will be some problems occurring because of the vertical normal velocity, normal free stream velocity. We will be having the tangential velocity and normal velocity now because of the angle of attack. There will be a normal velocity and also tangential velocity. So because of the normal velocity, normal free stream velocity, we will be having this downwash. This downwash will help you to reduce the wing tip vortices and also the trailing edge vortices. Okay, then
Okay.
and because of the downwash only, the Kutta condition is also get satisfied. Okay, then so here we can see the aerofoil session. Aerofoil is at an angle of attack alpha. This alpha is, they call it as geometrical angle of attack. So this geometrical angle of attack, it is a combination of effective angle of attack and so so effective angle of attack is the angle between the chord line and local relative wind. Okay, then this is the induced angle of attack, and also you can see the have you heard about this induced drag and all? Induced drag.
Yes, sir. Heard about.
Yes, sir.
And have you heard about this the lift will be the lift force? We will be drawing the lift force not like this. See, here the lift force is, this is the lift force, and we are drawing the lift force like an inclined, right? When the angle of attack changes, the wing is also changing. It will be inclined only. But we are not in drawing the, we are drawing the lift value. It is an perpendicular to the chord line only. But it is somewhat tilted now. It is tilted at some angle. That angle is called induced angle. Because of the induced angle only, we are having this lift is somewhat tilted back. And the induced drag term, it comes when it comes because of the when lift increases, automatically there will be some drag because of this particular lift. So that type of drag is called induced drag due to lift. Okay, these all things which comes from this induced angle of attack only. Okay, then so induced angle of attack, it is the hello, can you hear me?
Yes,
Yes.
sir. Yes.
Okay. So the local flow, the free stream air which hits the aerofoil, it is also, it is not in a parallel motion. Sometimes it may be in an inclined form. So it is somewhat inclined. May think that it is an inclined. Okay, assume maybe it is may straight, but it may not be in a horizontal. Like it may not be straight. Okay, so it may be inclined. So the inclined, the velocity of air which is inclined, or the angle of the wind is somewhat inclined. That inclined angle is called induced angle of attack. Okay, so effective angle of attack is the local angle between the local aerofoil and the relative wind. Okay, the induced angle of attack is the angle of the uh, local wind that hits the aerofoil. Okay, if the uh, local wind angle is 0, then that means it is straight, means there won't be any induced angle of attack. Okay, did you understand?
So can you please explain it again?
Okay, fine. So there are two things. One is effective angle of attack. Another one is induced angle of attack. Okay. So effective angle of attack, it is the angle between the aerofoil section. This is the aerofoil section. This aerofoil section and the local relative wind. So the angle between local relative wind and effective angle of attack is called effective angle of attack, and induced angle is the angle between that's the angle of the local relative wind. The local relative wind is inclined to some angle of attack. So the free stream velocity, we can say this is the free stream velocity, but it is inclined to the local relative wind. See, there is an angle between this. This is alpha I. So alpha I is called induced angle of attack. See this. This is the free stream velocity. V infinity is the free stream velocity, but it is inclined to the local relative wind. So this is called induced angle of attack. Okay. This is projected here also. That's why the lift is also somewhat inclined, and will be having the lift force at a somewhat inclined. That inclined angle is called induced angle of attack. Okay. So then next thing is induced drag. So induced drag is the most important part of the drag, because 25% of drag is contributed by induced drag only for most of the wings. So induced drag is drag due to lift. That is lift induced drag. We will call it as lift induced drag or induced drag. Drag which is created because of the lift created on the wing is called induced drag. Okay, then the next thing is the vortex filament. That's BIOT, SAVART and Helmholtz theorem. We are going to see only the formulas for this, because no need of this derivative part and all. So in the last class, last session and all, I have explained that the vortex filament. The vortex filament considered the straight line, a straight line which having vortex flow induced at some point is called vortex filament. That is straight vortex filament. That is vortex flow is a concentric flow induced over a specific point O, or point, whatever point maybe consider it as O or anything, whatever notations you give, you can give. So a straight line having some point vortex flow over some points is called vortex filament. But in general, the vortex filament, it won't be in a straight line. It will be in the form of curved. Okay, that's why here I am applying the vortex filament is here. You can see the vortex filament is curved. So in the last session also we have seen that consider a point here. That point is P. That is perpendicular to the vortex filament. The vortex filament has a vortex strength of gamma. The strength of the vortex is gamma, and you have selected a particular elemental length called dl. The distance from the point on the vortex filament to the point P is r. The induced velocity, when there is some it is in motion, the induced velocity over this particular point is dv. So for infinite length is length is from minus infinity to infinity. The induced velocity will be v equal to gamma divided by 2 pi h. This is an important formula, because they will ask questions based upon this infinite length. They will ask like this: what is the induced velocity? Specify the induced velocity for infinite length. The infinite length means v will be equal to gamma by 2 pi h. But for semi-infinite length means the length will be from 0 to infinity or 0 to minus infinity, whatever maybe it from 0 to minus infinity, or it is from 0 to infinity. If it is from then the equation for induced velocity v equal to gamma by 4 pi h. So v equal to, for semi-infinite length, v equal to gamma divided by 4 pi h. But for infinite length, v equal to gamma divided by 2 pi h. Please note this equation, these two equation, it is very important. So this is the BIOT-SAVART law. This BIOT law, we can apply this BIOT for a current carrying wire also, but we no need of that things here. Here we can see from BIOT law, dV equal to gamma divided by 4 pi into dl into r divided by r cube. This is BIOT law. That is taken from this filamental vortex filament, and but we need these two equations only. One is for infinite length, and another is for vortex filament for semi-infinite length. Have you noted down this two formulas, guys?
Yes, sir.
Okay, fine. The next thing is the Helmholtz theorem. So I am so I will so I ask one question. Just try to answer if you know. So there are what are the types of platforms for wing platforms? You know have you know the different types of platforms for wing. What are the different types of platforms? Okay, what are the different types of wings we have for an airplane?
Elliptical,
Elliptical, correct. Then
Dihedral, anhedral.
okay, horizontal. Okay, then
No, like based on what sort of criteria are you asking, sir?
based upon the shape, that means elliptical shapes,
Wedge,
rectangular shape.
wedge type, double wedge.
Yes. So we have basically we have two types. One is elliptical wing, another one is a rectangular type platforms. So these two platforms, whether the lift distribution is same for these two platforms?
No, sir.
no, sir.
No. There is a lot of variations of lift distribution over these two platforms. So we will be seeing the lift distribution for this type of particular platforms in this session. Okay. So for inviscid and incompressible flow, the strength of the, according to Helmholtz principle or Helmholtz theorem, the strength of the vortex filament is constant along its length. No matter the length, the vortex filament strength is same throughout. Then the vortex filament cannot end in a fluid. It must extend to the boundaries of the fluid or form a closed path. These are the two principles for Helmholtz theorem. Have you done any computational the CFD analysis in your BE projects and all? ANSYS CFD analysis?
No, sir, not yet.
Okay, fine. So, okay, fine. So, what? Why we are using test section in a wind tunnel? Why we are using a test section in a wind tunnel?
To test the material, sir. The properties.
To keep the flow steady
Flow pattern.
in that particular section, sir. So that the
Okay.
flow over the object is being steady, sir.
First of all, to test a material or study to study something. Maybe it is a wing or it is a airplane or something. It's an airplane model. Okay, or prototype model. Anything we are going to we are using this test section to study the product or prototype. Okay, so what we will call in a technical term, what we will call in a test section, it is a control volume or a boundary. Okay, correct, right? Yes, we will call the test section as a control volume where we keep the aerofoil or wing model to test it. Okay, so within the boundary only the airflow will be straight. After the test section, what will happen in a subsonic wind tunnel? Before the test section, what is happening? After the test section, what is happening? Anyone, please?
So the diffuser is kept, sir.
Diffuser is kept where?
It's after the test section, sir, because that is used to decrease the velocity.
Decrease the velocity of air leaving the section.
Yes, sir. So that when it is being emptied to the atmosphere, it's going to not create any sort of sound, sir.
Okay, fine. Then we are calculating any disturbance or any type of pressure force movements after the test section, we are not calculating that, right? Just we will see the pressure difference only, stagnation pressures, pressure points, static pressure points will be keeping in before the nozzle section, and after the in the diffuser section also we will keep it. Other than that, we won't calculate anything beyond the test section. So what the main thing I am focusing is, uh, uh, within the boundary only we will be calculating all those things. So that's why we are picturizing, or we are keeping a boundary, we are making a boundary, and inside the boundary we will be
Welcome to Wings
finding
of
all the things. That's why it is called
Advancing.
system, surrounding, and system and surroundings. This is a difference. So why I'm insisting that means, so here there is a vortex filament. Second point, the vortex filament cannot end in a fluid. It must extend to the boundaries of the fluid or form a closed path. Why they are mentioning that means, see the trailing vortices that is formed at the trailing edge of the aerofoil, it won't be at the trailing edge itself. It will move somewhat backward, or it will move downwards, and it will form a starting vortices at the later point. So if you have done any computational analysis, means you may know, we will be meshing the parts. That means we take an aerofoil in a computational analysis or ANSYS analysis. What we will do means, we take a aerofoil session, and we will be analyzing or see the performance, aerodynamic performance of this particular aerofoil. What we will do now, we will be meshing each. We will create a boundary. First we will be creating a boundary for a um, low speed aerofoils and all. What we will do now, we will be creating a C-shaped boundary layer. Okay, this but not a boundary layer, control volume. So C-shaped control volume we will be making. So after and we will be giving an after the trailing edge session, we will be we will have a extended control volume over that. Why we are doing that now? And we will be meshing the aerofoil into so many parts, so many, that means elements and nodes we will be meshing in that. And we will what I will do, or not I, most researchers, what they will do, in the trailing edge region and somewhat extended backwards, they will mesh in a fine mesh they will give. For what purpose they are giving that fine mesh is, after the trailing edge, the flow after the trailing edge, there is some disturbance, or some vortices formed at the backside of or the downstream of the aerofoil. In order to find that downstream vortices and all, or disturbance only, we will mesh the aerofoil after the trailing edge. We will be meshed it very finely. Okay, I will show you some images if I have. Now I don't have. Next session I will be showing that images and all. So now we can come to the session. So this Helmholtz theorem, it is used to find the lift distribution along the span of a finite wing. So here the span of the wing is B. Some from the origin or from the root. So we have for a wing there is a root and there is a tip. So this is a combined wing of left side and right side wing. So the origin of the wing is, this is the origin of the wing. So from here to here it is b by 2, and from this side to this side the length is b by 2. So this is the platform of the wing, and the lift, you can see a arc of this is the lift distribution over the surface of the wing. Okay, and the lift distribution is such that we will see later. So here what they are saying is, wings on a number of modern planes have different aerofoil sections all along the span with different values of zero lift angle of attack. This is called aerodynamic twist. So here we have a term called aerodynamic twist. What it so aerodynamic twist means, throughout the aerofoil section from root to tip, the zero lift angle of attack varies, because we will be having different aerofoil sessions at different session of the route. Now you have seen in your UG projects and all that at the route there the aerofoil will be one aerofoil, but at the tip the aerofoil is different. Have you noted in your design projects and all? Have you seen or studied this in your design projects and all? You may select different aerofoils for root and also as well as for tip. Have you anyone have you noted? You
Yes,
learned?
we have like aerodynamic twist and geometric twist.
Yes, two type of twists you have.
Two
So
types.
for yes,
Yes,
so the aerofoil sections, what we select for modern airplanes and all, we will be selecting one type of aerofoil at the root and another type of aerofoil at the tip. So each having different types of zero lift angle of attack. So so that is called aerodynamic twist. The because of the different angle of attack, there will be a small twisting. This is called aerodynamic twist. So one more thing, according to this theorem, the lift distribution at the tips will be zero, but the lift distribution at the root will be higher. So where the lift will be more means we will get more lift because at, more lift at the root and less lift at the near to the tip, and at the tip there won't be any lift. So this is wash in. The next thing is wash in and wash out. So wash in means angle of incidence will increase at the from root to tip. So the tip will be having higher angle of incidence and from the rather than the root. But wash out means root will be having higher angle of incidence, but the tip will be having lesser angle of incidence. So in wash in, what will happen? The tip will stall first. Wash out, what will happen means that root will stall first. So these are the conditions. Please note these conditions because this is needed. So for wash in, at the root, the angle of
Sir,
incidence will be lesser. Yes.
sorry, sir. Sorry to interrupt. I have a doubt, sir. If we if the lift distribution will be less at the tip, then why in case of forward sweeping they say that they experience the aerodynamic twist, sir?
I couldn't get you. Once again, repeat the question. So,
Sir, in case of forward sweepings, they say that the
mm,
wings are prone to aerodynamic twist.
yes.
So, so
Aerodynamic twist. Same thing only. See, aerodynamic twist means we will be having the different aerofoil sections. Because of the different aerofoil sections, we will be having different um, angle of zero lift angle at the tip and for the root. There will be change. That is only aerodynamic twist. The forward twist swept and the backward swept will be the backward set we will be using for in order to reduce the wave drag. You know that wave drag and that's a part, you know.
yes, sir.
Yes. So the backward subs will be the forward subs and all we will be using for the good maneuverability. That's what we will be using that forward sub and all. Okay. But for a backward sub, why we are using the backward sub means because of the backward sub we can reduce the wave drag because we need to fly within that Mach cone region. So if you fly the aerofoil, that means the aerofoil, the wing should be inside the Mach cone region. If it is inside the Mach cone region, then the uh, wave drag will be lesser. So that's why we are using backward swept. Forward swept is for maneuverability purpose only, mainly for turning. Then the maneuverability purpose, it will be better. Okay. So here, next thing is the washout. Washout means at the angle of incidence at the root is higher, and the angle of incidence at the tip is lesser. So here the in washout the root will be stalling first. Then the next thing is the geometrical twist and aerodynamic twist. So I have seen that geometric twist. So you have asked one question. So this twist and all, it prevents the stalling. That's why we are using this. So okay. So geometric twist means the angle of attacks are different at different regions of the aerofoil. That is from the root to tip. So the angle of attack at the root, it is one angle of attack, and it varies with the regions from root to tip. If the angle of attack is the angle of attack maybe at the root is higher and maybe at the tip is lesser, then it is called geometrical twist. The next thing is the Prandtl lifting line theory. So for why we are using this Prandtl lifting line theory means, from the name itself, it is clear that it is used for lifting. The lifting line is used for the lift distribution over the aerofoil. Here, what we will be having, we will be having a line. In this line, all the bound vortices are bounded to the this particular line filament, and the lift distributions are formed at the this particular line only. Then it is called lifting line. This theory will be called as lifting line theory. So it may be applied for 3D wing section. The main application is we can apply the Prandtl lifting line theory for 3D applications. And so for in a Prandtl lifting line theory, you can see the bound vortices, and there are two types of vortices. Totally, there are three types of vortices. One is bound vortices, trailing vortices, and starting vortices. This bound vortices and trailing vortices are it is a the combination of both bound vortices and free trailing vortices are called horseshoe vortices. Trailing vortices, because of the downwash, the trailing vortices, starting vortices, because of the downwash, the trailing vortices are moved somewhat downstream, and a curl is or vortices uh, formed at the downstream, that is called starting vortices. So the vortex filament of strength, this is gamma, that is bound to some location in a flow, is called bound vortices. That is, here consider this is the plan form of the wing, and if the bound vortices is bounded to the surface at some location, then consider this as a location, then it is called, it is, that means the vortex that is bounded at some particular location, that is called bound vortices. Then free vortices are formed at the trailing edge. This is from the Helmholtz theorem only. We will be seeing the free vortices, that is free vortices that move with the same fluid elements throughout the flow, that won't be stagnant at a particular region, it moves with the flow. That's why that vortice is called free trailing vortices. Free vortices are vortices that won't be stagnant at particular region, it moves with the flow. That's why it is called free vortices or free trailing vortices. Why they are calling it as free trailing means it will be formed from the trailing edge of the airfoil or wing. Okay. Then the combination of bound vortex plus two free vortexes, the shape will be like a horseshoe. That's why it is called horseshoe vortexes. Okay. So here see, this is the line which denotes the vortex line filament, and this vortex line filament, the vortex is bounded over the line, and that's why it is called bound vortices. And the span of the line is from origin, it will be b by 2 here, and this is minus b by 2 and plus b by 2. This is a free stream velocity. So the lift, so this is the induced velocity, that is over the, because of this bound vortices. So the induced velocity at this semi-infinite vortices are w of y equal to minus gamma divided by 4 pi b by 2 plus y minus gamma divided by 4 pi b by 2 minus y. So in while combining, we will get w of y equal to minus gamma divided by 4 pi b by 2 the whole square minus y square. So consider this is the line where the horseshoe vortices, this is the type of horseshoe vortices. So consider like this. So one horseshoe vortices is formed like this, and consider some there are so many number of harsh vortices adjacent to this sides, this line. So if it is formed like this, we will be having the lift distribution over the aerofoil, because this bound vortices, it will have some vortex strength, that is vortex strength is gamma. So because if we are having the vortex strength gamma, means we will be having lift from Buta-Jaggers-Cavey theorem, we will be having lift at this bound vortices or this harsh vortices, and adjacent to that side we will be having another one bound vortices. So this vortices will be also having some gamma strength gamma, and adjacent to this side, next one, it will also have one gamma value. So each bound harsh vortex, it has one vortex strength, that is gamma. So this because of this vortex strength, we will be getting lift, that is L equal to rho v gamma. So first we need to find the gamma value. After finding the gamma value, we can directly find the lift value. So if a number of bound vortices that coincide on a single line, if a number of bound vortices that coincide on a single line is called lifting line. This lifting line, that is that's what I told. If number of bound vortex, this is one bound vortex, two, so there are number of bound vortices that coincide on a lifting line. So this is the lifting line. In that lifting line, there will be, so it also each one have its own lift. So all together we will see it like a lift distribution or distributed over the particular line. Okay, so lift distributed over the particular line is called lifting line. The theory is called lifting line theory. So here you can see the lift distributed over this line, and at the root the lift is high, but at the tip the lift will be 0. So this is the bound vortices. So here you can see this first one, d gamma 1. This is the strength of this bound vortex. It extends from the whole length of the span. And the second one, that is from E to B to E. This is B to E, second vortex. That is the strength of this bound vortex is d gamma 1 plus d gamma 2. And third one is from C to D, and the C to D, the strength is from, it's like this. So it is a combination of both d gamma 1 plus d gamma 2 plus d gamma 3. So that's why you can see this the CD, it has the greater strength because it is a combination of all three things. But then adjacent to that, it has a combination of both d gamma 1 and d gamma 2. But the last one near the tip, only it contributes from that single vortex only, or single bound vortex only. That's why it is the strength of that bound vortex is d gamma 1. So altogether, while drawing the lift distribution curve, we will be drawing like this. So from this, it is clear that over the root region, consider this is the root. From this origin, it will be we will be consider this is the root. So the root region has more lift, while the tip region, it has less lift. So the total velocity induced at y naught by the end of trailing vortex sheet is w of y naught equal to minus 1 by 4 pi minus b by 2 to b by 2 d gamma by dy divided by y naught minus y. So the induced angle of attack is alpha I of y naught equal to w of y naught divided by v infinity. This we got from here. So alpha I equal to this angle alpha equal to what? Sin alpha equal to w divided by v infinity. So I am considering this w as w of y naught. So therefore alpha equal to sin alpha equal to w of y naught divided by v infinity. Since the angle is induced angle is very small, so sin alpha will be reduced to alpha. Therefore alpha equal to w of y naught divided by v infinity. That's what it is here. So alpha I of y naught equal to minus w and this minus sign indicates that the downwash is in downward direction. If it is the downwash is in upward direction, then it will be positive. If it is in a downward direction, then sign will be negative. So here substituting the values of w of y naught, we will be getting alpha of y naught equal to 1 by 4 pi v infinity integral of minus b by 2 to b by 2 d gamma by dy divided by y naught minus y. Actually, these things and all we don't want these things and all, because in maximum questions which I have seen, you will be there. They are asking questions from thin aerofoil theory and cambered aerofoil theory, and also from induced drag. Induced drag formula. You all know the induced drag formula that we will be seeing next classes. We will be solving some problems for that induced drag and all. They are asking some questions from induced drag, and also from induced zero lift line. Then the moment coefficients, lift coefficients, pitching moment coefficient, they will be confusing us like a pitching moment coefficient about some point. But the same thing, moment coefficient about some point. Maybe it is a leading edge, or maybe it is a trailing edge. So alpha I of y naught equal to 1 divided by 4 pi v infinity integral of minus b by 2 to b by 2. Yes. Hello.
Hello, sir. Sir, can you just go back to previous slide, sir?
Yes.
One more, sir. One more slide. Hello, sir.
Slide only.
One more previous.
Okay.
One more, sir. Sorry, one more. First, Randall's. Yeah, sir. Sir, this one horseshoe vortex. I'm getting confused, sir, with the directions of flow. Like vortex will be like on the surface of the wing, right, sir?
Yes.
So vortex, this leads to formation of more drag, right, sir?
Yes, because of the trailing edge, we will be getting more drag only. That's why we are using winglets at the wingtips and all. Wingtips vortices will be getting now. So we'll be using the winglets at the for the whole
Yeah,
wing.
yeah,
Yes.
yes. To reduce the drag.
Yes. So here you can see the direction of vortex is in opposite direction for these things. Here you can see this. See.
Yeah.
That means at the trailing edge, no, that is a wingtip. The flow from the bottom surface at the left end, it will come in the direction of like this only. That's why the vortex is in this direction. But in the right side wing, it will be come from opposite direction. That's why the vortex
Yeah.
direction is like this. Okay.
Okay. Okay, sir.
Fine. Now shall I change?
Yeah. Yes, sir. Yeah.
So the lift coefficient equation for this aerofoil section is CL equal to A naught alpha effective of y naught minus alpha L equal to 0. That is equal to 2 pi into alpha effective minus alpha L equal to 0. So from after finding CL, we can find the lift of the particular section. So L equal to half rho infinity V infinity square. This formula you know, S into CL. S is C. That is equal to by Kuta-Jankowski theorem, we know rho equal that is equal to L equal to rho infinity V infinity square gamma of y naught. So from that CL equal to 2 gamma of y naught divided by V infinity C of y naught. This is from the cross multiplication and all we will get. So then you know that here we have the formula like this: CL equal to 2 pi into alpha effective of y naught minus alpha L equal to 0. So we found that CL, by substituting that, we can get this alpha effective of y naught. So alpha effect equal to gamma of y naught divided by pi v c gamma c of y naught plus alpha L equal to 0. Now I am substituting all those things. And finally we will get alpha of y naught equal to gamma of y naught pi v infinity c of y naught plus alpha L equal to 0 of y naught plus 1 by 4 pi v infinity integral of minus b by 2 to b by 2 d gamma of by dy divided by y naught minus y. So this is the fundamental equation for Prandtl lifting line theory. But you won't be asking, they won't be asking questions like this and all. They won't be here. There are no such problems for. Sorry. They will be asking some conceptual questions from this session only. Okay. So now we will be solving the problem which we dropped for cambered aerofoil. So here you can see the NACA 441 aerofoil which has a mean camber line given by Z by C equal to 0.25 into 0.8 x by C minus x by C of whole square for 0 less than or equal to x by C less than or equal to 0.4, and also another one equation for the limit 0.4 to 1. Please note this question because we are going to solve this now. Hello, anyone?
Yes, sir.
Yes, sir.
Noting.
Okay, please note it down. So we here by using thin aerofoil theory, that is a cambered thin aerofoil theory, we need to calculate the alpha L equal to 0. Suppose they ask the question like this: find the zero lift angle of attack for thin aerofoil theory for a symmetrical aerofoil, that is 001 aerofoil. Means what you will do, and they are not giving any choices. You need to find the answer. What will be the answer? Do we have any formula for the alpha L equal to 0 for a symmetrical aerofoil? Do you understand my question, students?
Please repeat me.
No, sir. Once again.
One second, I will repeat. So, in your GATE exam questions, suppose they ask, find the zero lift angle of attack for NACA 0012 aerofoil, that is a symmetrical aerofoil, by using thin aerofoil theory. And what will be the answer?
It will be 0, sir.
Yes, it
Hello?
is 0 because the condition is symmetrical aerofoil doesn't have zero lift angle of attack. The angle of attack, zero lift angle of attack is 0. That's why.
Yes,
So
sir.
answer is 0. Okay.
0.
So here they have given on 441 aerofoil. This is a cambered aerofoil having a mean camber line equation is given. This is the mean camber line equation. From this equation, we need to find the zero lift angle of attack value. Okay. So first of all, we need to know what is the zero lift angle of attack formula. So okay, I will solve this problem. So we have a equation like Z by C. So see here, but the zero lift angle of attack for from a thin aerofoil theory, the expression it gives alpha L equal to 0. You can see the slide now. Alpha L equal to 0 equal to minus 1 by pi integral of 0 to pi dz by dx cos theta naught minus 1 into d theta naught. That is cos theta minus 1 into d theta. Okay. So we need to convert this alpha L equal to 0 equation. That is z by c into dz by dx value like this. So we have the equation. Sorry. That is z by c equal to 0.25 into x by c. So guys, you can also solve this problem. I will tell how. First of all, we are having that z by c equation only now. First we are having one z by c equation. There is two equations. We need to convert that z by equation by dz by dx. We should differentiate the equation with respect to x. So by differentiating the equation with respect to x, we will be getting some. Students, can you able to hear
Yes,
me?
sir. Yeah.
What we need to do now?
Yes, sir.
We need
Listening.
to, yes, we need to differentiate with this equation with respect to x. We are having one x by c
Yes.
value that we need to change that. First we need to differentiate this equation. So first, then we need to convert see that in here we have the equation alpha L equal to 0 equal to minus 1 by pi integral of 0 to pi. So we need to change the coordinates to or the limits to 0 to pi. But we are having the limits here. Limits of this problem as 0 to 0.4 and 0.4 to 1. We need to change the limits from 0 to 1, 0 to pi. Okay. Right away, first we need to do this. So I will be solving this. You also try to solve this problem by in your note and all. So d is set by it was somewhat difficult to draw like this. Sorry, write like this. Sorry, please adjust for some moments.
Sir,
Yes.
sir, we have to shift C towards the right hand, no, sir?
One
Hello,
second.
sir.
One second. Yes. Yes.
Hello.
Yes.
Hello. Sir, I am getting around 0.25 into 0.8 minus x by 2c, sir.
Yes. Correct. Then for second equation also
Correct, sir.
0.111 into 0.8 minus 2 into x by c. That this two equation you got.
So second equation I have not solved, but the first equation I have solved, sir.
Okay. Solve the second equation also. Same thing only. Same. The equation is same only. Only the outside the value of 0.111 is changing.
Yeah, sir. Yeah.
Yes. So first of all, everyone please differentiate with that. So after differentiation, what we need to do is we need to convert that x by the limit values. So for that we have equations that x by c equal to we have on equations now like this. That is x, sorry, I will show in slide itself because it is not working. So here we can see that x equal to c by 2 of 1 minus cos theta. Okay. Don't put it as theta not and all, just put it as theta itself, no problem. Because we are having only x by c here. So take it as x equal to c by 2 into 1 minus cos theta. So from that cos multiply this. So it will become x by c equal to 1 by 2 into 1 minus cos theta. Okay. Can you able to hear me? Just write this down. So x equal to c by 2 into so see here x equal to c by 2 into 1 minus cos theta. From that we can do like this, x by c equal to 1 by 2 into 1 minus cos theta. Now you substitute the limits because no need to substitute the 0 values, that it will be 0 only.
Sir, same answer, sir, but to say. Sir,
What
second
same
one.
Second one for differentiation, you found the differentiation that dz by dx are
Yeah, sir.
same thing only. Only the thing we need to put that
Constant
outside
0.11
into
multiplication.
0.8 minus 2 by 2 into x by c. Okay.
Yeah.
So next thing what we need to do is we need to convert the limit. After that only we can substitute that in alpha L equal to 0 equation. Okay. So first of all substitute that take the equation x equal to c by 2 into 1 minus cos theta. Okay. In that x by c value just put 0.4 because we are having the limit as 0 less than or equal to x by c less than or equal to 0.4. Substitute the value of x by c as 0.4 and find the value of theta.
Zero, sir. Angle. Theta.
Angle 0. No. It won't come 0. What value you put
X
for
by
x by c? X by c you put 0.
X by c 0.4. You told no. Hello.
Yes, 0.4 only. It won't come 0 na.
Considering first equation, no, sir.
No need to consider the first equation. You just put the value in c x equal to c by 2 into 1 minus cos theta equation. You just substitute the x by c
Oh,
value in this equation. Okay.
Yeah, yeah.
sir, 78 or 46.
78.46, sir.
78.46. Convert that into radian.
Hello, sir.
Yes.
1.369 radians, sir.
1.36 radian. That is the correct answer. Okay. So the limit is 0 to 1.36. Also substitute the value as 1 and find the answer. In the same equation, substitute the
Yes.
value as 1, x by c value as 1 and find the answer.
3.14, sir. Pi, sir.
5. Yes. So now we found that the limit from 0 to pi, right?
Yes, sir.
Yes. See here. Uh, so here see alpha L equal to 0 equal to minus 1 by pi integral of 0 to pi. So the limit is satisfied. So we found the limit from 0 to pi. Now we need to substitute the equation and find the answer. Okay. Now please substitute the dz by dx value like this. See first alpha L equal to 0 equal to, I will say, minus 1 by pi integral of 0 to pi 0 to, first we need to put 0 to 1.36. Okay. Then plus 0. Sorry, then 1 point, then integral 1.36 to pi. Likewise we need to put. Then dz by dx value for for limit 0 to 1.36, you need to substitute the first equation, and from for limit 1.36 to pi, you need to substitute the second equation.
Sir, would you please just repeat, sir?
See for so here we have the, for this formula alpha L equal to 0 formula, we have the limit values from 0 to pi, but we here we have two equations for dz. So the first equation, the limit is from
Sir,
0 to,
what, sir? Last question.
yes, yes, substitute the equation, only the dz by dx equation there. Okay. First you substitute like this, minus 1 by pi integral of 0 to 1.36 into 0.25 of 0.8 minus 2 into x by c. Okay. Into cos theta minus 1 into d theta. So in the x by c value, you substitute like uh, uh, this 1.36 and 0. Okay. Then in the second equation, just substitute 0.111 into 0.8, that equation. Okay. And one more thing. So suppose they ask questions for a zero lift angle of attack means for a cambered aerofoil, the answers will be in negative values only. It won't be in positive value. It will be in negative values only. Okay. And it will be minimum value. The degree will be minimum. And also finally, if they are giving some values for this, that means the answers like it is the answers are in degrees means you need to convert the value you find, you will be getting it in radian only. After that, you need to convert that radian into degree. Students, can you able to hear me?
Yes, sir.
Can you able to solve that problem?
No, sir.
So in the morning section, I have given one problem. Did you solve that problem? I'll ask you to finish it by evening. Anyone solved that problem? So guys, listen. So listen. You will be just substitute the value for dz by dx in that equation in the alpha L equal to 0 equation and find the answers. Okay, the answer will be answer for alpha L equal to 0 will be it should be in the degree only, that you will get answer in radian, convert that into degree. After that, uh, see that if your answer is correct, you will be having the value as a negative value, and it will be in a that like up to 3 degree minus 3 degree, like this you will get 1 2 3 0, like this you will get. Okay, so try to complete this. We will be seeing that in a next class. Now try to solve it. If you have any doubt means now please ask.
Hello, hello,
Yes.
hello. Yes, sir. Sir, please share the PPT on WhatsApp.
Yes. Is it okay? Anyone finished? The last problem itself, I have told the trigonometric function is that is the integral of cos square theta d theta, that is equal to 1 by 2 sin theta cos theta plus 1 by 2 theta. Okay, and also integral of cos theta d theta equal to sin theta. In this problem also you will be facing the same trigonometric functions like this: integral of cos square theta d theta, integral of cos theta d theta, integral of cos cube theta d theta. So if you come up with that problems means just uh, write the answers for the write the formulas for that and use that trigonometric formulas and solve the problems. Okay.
Hello, sir.
Yes.
Hello, sir.
So I couldn't hear you.
Sir,
Huh.
hello. Now, sir. Sir, actually, the power went, sir, and battery is down. So, is the session over or it's?
I couldn't hear you. Please. Hello.
Hello, sir. Now,
You're asking the session is over.
yes.
Yes, the
Now, can
session
you
is
hear me,
almost
sir?
over. Almost over. Just you are if you are if you are having any
Because
doubt means that only I am waiting.
no, sir.
So please, it is not clear. Your voice is not clear. Just type in this chat box so that I can able to know. Aishwarya ma'am? Ma'am? It is almost over. Okay, okay, ma'am. If they are facing any problems, means please intimate me.